can see the slides if you press the share button. Excellent. I think you're muted, Matthieu.
Yeah, sorry. And now can you hear me?
We can hear you. Can you try turning off your camera just in case the bandwidth is limited? No,
yeah,
no,
sure.
Actually, perfect. Take it away, Matthieu, then.
Okay, so thank you. Sorry for the computer problem. And I will start by thanking warmly Mark and Young for the invitation and people involved in the organization. So today I will talk about Munchausen reinforcement learning, named from the Baron Munchausen, and the picture is from the Baron Munchausen. And I will talk about similar things. So the thing is that bootstrapping values is really something which is ubiquitous in reinforcement learning. And here is how one can derive or explain Q-learning. If you knew the optimal Q function, you could regress it by updating the estimate like this. That is, you target the optimal Q function, but you don't know it. And would you know it, you would not have to compute it. So the idea is that if you know the optimal Q function in the next state, you could do backward induction and say that you would try to regress the reward plus gamma, the max of Q value in the next state. But you don't know the Q value in the next state, so you replace this guy by an estimate. And this is how Q-learning works. And this is very ubiquitous in reinforcement learning in the sense that it uses Bellman, so it uses TD, and if it uses TD, it uses bootstrapping. But what we bootstrap is the value in reinforcement learning. And the idea is that maybe there are other quantities that we could bootstrap. And there's one natural quantity is a policy. And the core idea of this work of Munchausen reinforcement learning, or what we call so, is to just add the log policy to the reward, and that's it. And why doing so would be interesting. Assume that you know the optimal policy and pick a deterministic one. The log optimal policy will be 0 if the action is optimal, and it will be -infinity if it's suboptimal. So this is a very strong learning signal. If you have this, you have solved the problem. But we don't know the optimal policy, so we just use the current estimate of the policy. So the idea is to augment the reward with the scale log policy, which requires stochastic policy, but we will deal with this. And this is different from maximum entropy reinforcement learning because it will subtract the log policy and not add it. And this, as I said before, it's named as reference to Baron Munchausen. So as a case study, we'll see how to modify the classic DQN algorithm to take into account this Munchausen term. So I guess that everybody knows how DQN works. And what we'll do, we'll just modify the regression target of DQN. So if you look at the first equation here, it's the regression target, it's the reward plus gamma, the expectation of action given the current policy of the Q value, and the current policy is greedy according to the target network. So basically, it's max over action of Q theta, but a maximum is an expectation according to the greedy policy. Now, we need a stochastic policy to use the Munchausen ID. So to get a stochastic policy is a simple way. The simpler way, maybe, is just to add some entropy regularization that will say I want to maximize the reward, but I want to have high enough local entropy for my policy. If you do it properly, you end up with this update for soft DQN. And here you have the policy now, it's a soft max over the Q value up to some temperature tau. And you just have to modify removing the log policy to the Q value. For those who know soft actor critic, it's the same algorithm, except that you don't have to actually make the greedy step in a discrete action setting. And once we have done this, we just add the Munchausen term. That is, we add to the reward, we add the log policy of the current state and action. And pay attention to the fact that here we have minus and here we have plus. So it's not just doing entropy regularization, it's more than that. And that's it. We have a new algorithm by just adding two things in the regression target. So the question is, how does it work? And it works pretty well. So here you see the result on the Atari game. We use dopamine to modify, you use DQN from dopamine and the setting from Marshadow, that is with sticky actions and so on. And in orange, you have DQN. And in blue, you have Munchausen DQN. And these scores are human normalized score, mean and median, average over or median over the 60 game of the arcade learning environment. And as baseline, we also have C51. C51 is a distributional algorithm, reinforcement learning algorithm, the first one, and a strong baseline for reinforcement learning agents that are not based on a distributional array. And we know that Munchausen DQN can do better than C51, even if it doesn't use the distributional ID, and even if it's simply a simple modification of DQN. If we look at the per game improvement, what we can see, I don't know if it's really relevant here, the games where it doesn't work well are hard exploration and sparse reward game like Montezuma or Venture or Private A. And the thing is that you bootstrap your policy, that is, you will add some bonus for action you think are good. And if you don't get a reward, you don't have a signal to reinforce, so you will reinforce the noise of the initialization, basically. So this is not well designed for a hard exploration game with sparse reward. But for the other games, it helps quite a lot. And as an example of the generality of this approach, we also modified the IQN. So implicit quantity network is a more recent and very efficient distribution or reinforcement learning algorithm. And we did exactly the same. You just add some entropy, and then you add the Munchausen term, and you get an algorithm. And we see that it works well. We have a clear improvement over IQN, and the green curve is rainbow, the rainbow from dopamine. So not all the components, but still Munchausen IQN works better than a rainbow, with only the Munchausen term, no prioritized experience shortcut. So the question is, why does it work? And there are two main reasons. The first reason is that it performs implicit Kullback-Leibler regularization. So Kullback-Leibler regularization is good. It comes with very strong performance guarantees, but these performance guarantees relies heavily on the fact that you don't do errors in the greedy step, and we avoid it with this approach. And the second aspect is that it increases the action gap. The action gap is the difference between the Q value of the best action and over Q values. And the bigger it is, the less you might suffer from estimation error. And indeed, Munchausen generalizes advantage learning. And we can also quantify analytically the increase of this action gap. So first, about the regularization aspect. Here you have an abstraction of Munchausen reinforcement learning. If you just take the black part of the equation, what you got is DQN. You compute the greedy policy right there, and then you update the Q function, and the target is reward plus gamma as expectation of a new state of the max over Q value. Then with the blue part, you add the entropy regularization, and with the red part, you add the Munchausen term. And the first part, the greedy step, the solution of this is just a convex conjugate of the entropy. The solution of this is the softmax over Q values, and it can be computed analytically given discrete actions, even with neural networks. And the error term here is mainly the difference between what you will do in the ideal case and what you do practically. Now, if we look at what is Scalar regularization in reinforcement learning, you can frame it like this. So you take a value iteration scheme, you penalize the greediness of the policy by a Kullback-Leibler term between the policy and the previous one, and you add some entropy to get stochastic enough policies. You modify the evaluation step accordingly. And this is quite general, because if you put alpha to zero, you will get entropy regularization. If you put alpha to 1, you will get Kullback-Leibler regularization. So something which is very reminiscent of algorithm like TRPO or MPO. And you can combine both. And the solution to this greedy step can be computed analytically. And the new policy will be proportional to the previous one with an exponent alpha time exponential of qk over tau. So you can compute analytically this, but you cannot compute it analytically if you only use neural networks. Because if you look at this, you can use an induction argument. So pi k will be proportional to exponential qk minus 1. So this whole guy, if you take alpha equal to 1, will be proportional. It will be a softmax according to the sum of all past q functions. So you can do this in a lazy way with a linear parameterization, but when you use neural networks, you have to remember all past q functions if you want to do this analytically, and it's not convenient. So the classic approach here is to have an actor in addition to the critic. So you parameterize the policy with a neural network, and you solve approximately for the greedy step by doing a gradient descent or gradient ascent here. But you lose the nice properties because if you use neural network, you have some additional error term here. And the thing is that both schemes are indeed equivalent by just writing a reparameterization of the q function. So the q prime k here is equal to qk here minus the log pi. So these schemes are equivalent. So the bounds we have for this one apply to this one. And the bound is the following. So here I just give a supermem bound, which doesn't really make sense in a deep learning setting, but which is easy to read, and you have the more general component-wise bound in the paper. But what you bound is the distance between the optimal q function and the q function of the policy, which is outputted by the algorithm. Here you have 1 over 1 minus gamma is the average horizon, the average optimization horizon of the MDP. So here you have a square dependency to this horizon. And if you look at the bound for Munchausen, you only have a linear dependency to the horizon. And this is much, much better. And very few reinforcement learning algorithms enjoy only a linear dependency to the horizon, and even fewer that are practical. Here you have the error term. And in DQN, what you pay for is roughly a moving average of the norm of the errors. So even if your errors are zero mean, bounded, this scheme cannot converge. The only way to have this scheme converging is to have the norm of the error going to zero fast enough. When you look at the bound, the error term, the bound for Munchausen DQN, what you have is that you have the norm of the mean of the error. And the absolute value and the sum are not commutative operator. Here, this means that if your errors are zero mean and bounded, then this guy will go to zero, and you will have convergence. And the last term is the convergence rate, in the sense that it gives the convergence rate where you do no error. And it's faster for DQN than for Munchausen. But it makes sense because you add some entropy Kullback-Leibler regularization, so you ask for the algorithm to be more conservative. But when you look, this is an illustrative example, a numerical example of the bound, where we have a problem with a tabular representation, which means that you can represent exactly the Q function, but the error comes from sampling. And when the error comes from sampling, you have a marginal difference, so you will have a concentration of zeros. And in blue, you see approximate value iteration. It doesn't work. It doesn't converge. It cannot converge. And when you do Munchausen or Kullback-Leibler regularization, it converges, and the different value are for different value of the different curves are for the different value of the temperatures. And the last thing is increase of the action gap. So here I recall the Munchausen updates, And so we add the log policy, but the policy is a softmax of a Q value. So we can compute this analytically and see what it gives as a function of the Q value. So it's the Q value minus the log sum x of the Q value. And this log sum x is a smooth maximum. And when you take the temperature going to 0, what you get is that you get advantage learning. And advantage learning is an algorithm introduced by Mark and colleagues, inspired by close to an algorithm introduced by Lehman Bird. And the nice thing about this algorithm is that it increases the action gap. But in previous works, the increase was not quantified. And the good thing is that with Munchausen, we can quantify the increase of the action gap. And so the action gap, I said before, is the difference between the maximum for any state, the maximum Q value and the Q value of our actions. And basically, you will increase the action gap by a ratio 1 plus alpha over 1 minus alpha. And the propagation of error bounds are better if alpha is close to 1. This bound is also better if alpha, this quantity is better if alpha is close to 1, but in the limits, the action gap will be infinite, which is normal. But an infinite action gap means that you will have to estimate an unbounded function, and it's not desirable. So the good thing is to take an action gap close to 1, say 0.9. So I think that I'm running a bit out of time, so I will skip the ablation study. So just we have an ablation study that shows that compares Munchausen to advantage learning DQN, soft DQN, and so on. And versus baseline, this is mainly an aggregation of the results I've shown before. So to finish with, Munchausen reinforcement learning is a quite simple idea. Just say add the log policy to the reward. You can get it by modifying existing agent, and the modification in DQN is really a matter of not even a number of lines, but a number of characters. It's theoretically grounded in the sense that it performs implicit Scalar regularization, and you have a strong performance bound. And the interesting thing, I think, is that this approach is really interesting because we work with neural network. With a linear parameterization, you can just do pullback label regularization in the standard way. It will work the same way. It is really interesting thanks to the use of neural networks. And it also increases the action gap with theoretical quantification, an asymptotic one without error, but still it's quantified. And it works very well because if you add this to IQN, it's better than Rainbow. So if you want to know more, you can check the paper for the algorithm, the previous paper for the analysis, and both should be presented at NeurIPS. And if you want to try it, the code is open sourced on the Google GitHub. Thank you.
Thank you so much, Matthieu. This is fantastic. Well, let's open up the floor to questions. We have about 10 minutes.
Well, I guess I can ask a question. I mean, I also really love this work as well. Seems like today is that kind of day. So I'm just like really wondering, like, if these error terms that you have in the bound showing up, do they really have the same meaning as before? Because now you're trying to estimate sort of a different loss function that is not just rewards, but also these KL divergences, and maybe they're on a different scale, and maybe you're adding like larger errors together.
Yes, you're right. But by increasing the action gap, you will increase the range of the function you try to estimate. And in the limit, you know that the range of function you're ideally looking for is infinite. So if you try to estimate an infinite function, you will do a bigger error, for sure. And that's why I said you should not have 5 to 1.
Right.
But still, the thing is that the estimation problem is maybe a bit harder, but a bit easier because you increase the action gap, you can afford more error. But the good thing is that you will have this compensation of errors. So as long as you don't try to estimate unbounded quantity, you will have a compensation which is possible. And you can write, if you have a tabular representation, a generative model, it's quite easy to write the bounds. In the more general setting is harder, because what you average is a random error of the whole function, and what you will control when you do statistical learning theory is the average error according to some norm of one iteration. So you cannot say much about how this quantity will behave. But you know that sometimes you will overestimate, sometimes you will underestimate, and in average, you will have a stronger balance. And it requires empirically.
Yeah, right. So I understand that before you basically like had to fit two objects, like a policy and the value function. Now you don't have to deal with these approximation errors in terms of the policy, but now you have to estimate these log terms or these Ki divergences in terms of the squared 2 norm, right? Which may not be like a very natural way to measure errors in the policy space.
You don't have to. You have no longer errors in the policy space.
Yeah,
you
right.
only have
Because you push that into the Q functions, right? But you still have.
Yeah.
If I can jump in, I think maybe Gerke, your discomfort is maybe coming from looking at a single action, right? The log policy of a single action. The KL itself might be a little better behaved, and maybe that's like, I'm assuming the analysis is done with the KL divergence and not the sample-based log terms.
You might take caution. You should be cautious about numerical stability when you do log of softmax or these kind of things. But roughly, the log policy is an advantage, is an action gap.
Yeah, that's right.
So it's well behaved. And I can tell you what should be the maximum range of the action gap according to the original problem. If the action gap is delta in the original problem, it will be a delta over 1 minus alpha. So if you take alpha to 0.9, you have a time 20, it's still okay. But the thing is that this paper is really about discrete action. If you go to continuous action, if you fit a Gaussian policy and you're far from the mean with a small variance, you will have clear problems. But all the arguments, all the experiments we did, and the theoretical justifications hold in the case of discrete actions.
Right. Okay. Well, thank you. Okay, I'm gonna let others ask questions as well. Thank you, Matthieu.
We had a question from Nan, or a comment from Nan, about linear horizon dependence, and Amir Masood also wants to ask a question.
Should I start, or?
Go ahead.
Okay, great. So I enjoyed it. I mean, the idea is very cool and nice. So I kind of have a kind of speculative question. Like, it is from the first step, or one of the first step was adding this log of pi term. And so you interpret it as some form of like additional reward. So what I was thinking is that, what if you just define another MDP with that reward, or another agent that only receives that log pi term and not the original reward, and just train it and consider that log pi of another agent as its reward? So what would happen? I mean, have you thought about it? Is it something meaningful at all, or is it just random?
So this is something we have roughly tried, but for different reasons. The thing is that you have a coupling between the log policy term and the reward. It's not like having two different rewards, because the reward depends on the policy, that depends on the Q function, that depends on the reward. So you have this kind of coupling. And we thought about separating the two terms, but for different reasons. The reason is that when you do things like Atari, the scale of reward is important. So in Atari, you have to clip the reward between -1 and +1, or you have to use overclip of thing to handle this. And here we add something. So we were thinking that adding this stuff could harm the behavior of the problem, which is not the case. We don't clip the additional term, or maybe we clip it for numerical reason, but not that much. And we were thinking about, you have a paper by DeepMind, which is called Agent 57, where they do superhuman performance on all Atari games, and at some point they use exploration with intrinsic reward, and they use separate networks to learn the two rewards because they have different scales. And this is something I think we thought would be useful in our case, but the fact that you have this coupling between the bonus and the Q function means it's hard, because the Q function you will learn in the over MTP would depend on the first one. So you should handle this coupling. So it's not that straightforward, but it could be an interesting direction for sure.
Thank you.
Fantastic. We'll take two more questions. One for comment from Nan, and then there's also a question on the Q&A, and then we'll move on to Peter after that.
So maybe I can just say a little more related to my comment. So you know, I think I've also looked into the linear horizon dependence recently, and you know, one thing I realized from literature is that Bruno Schwerer and his collaborators have this paper telling you that if you do something like ABI, but you outputted the non-stationary policy, you also get linear horizon dependence. And sorry, I missed the first part of this talk, but I think I read the paper and remember you also have to keep around some of the history, like functions from past iterations. So that makes me think that maybe it's better to do a comparison to non-stationary, like the non-stationary version of DQN or something. Have you tried that? I'm actually curious to see whether non-stationary DQN actually perform any better than like stationary DQN.
So yes, indeed. I know well Bruno. I know well this work on non-stationary policies, and in this work, he indeed showed that if you do value iteration or policy iteration, the square dependency to the horizon is tight. And we tried, not in the context of this work, we tried it 1 or 2 years ago. We tried to write a non-stationary DQN, and it doesn't work at all. We didn't manage to make it work. And it was with a student that I co-advised with Bruno. So, no, it doesn't work. Nice theoretical thing, but not practical one. But you have also something called PSDP, Policy Search by Dynamic Programming. The paper is a bit old. It does roughly the same thing, but on an infinite horizon setting, it's quite close to what Bruno did. And they had some experiments, but it's basically you go back to backward induction. And for this to work, you have to start from the end. The thing also is that you don't have this compensation of errors. And I think the thing that makes it works is the compensation of errors. Because I'm a bit lying in the sense that the nice bound I shown with linear dependency is for alpha equal to 1, and alpha equal to 1 is not the thing that you do when you do deep learning. And with alpha lower than 1, but still the compensation of errors.
Great. We're almost out of time, but Matthieu, I would like to ask this question, pose it to you. This is a question from Mayank Bashkar saying, so we could use the KL divergence, you know, as the term as you've done here. Could we use a different divergence between policies, and would we get similar results? For example, the total variation.
So no. And why? The reason why is that at least for the analysis, for my understanding of the bound, and I did them, so I think I understand them well. The thing is that you don't use the Kullback-Leibler divergence. What you use is that you say, as I said before, when you use the Kullback-Leibler divergence, it's like saying that your policy will be greedy according to the softmax of the sum of all past Q functions. And this is really what you use to prove the bound. And that's why when you do error in the greedy step, it's no longer the case. You no longer have this equivalence between I put Kullback-Leibler regularization or I am softmax according to the sum of Q function. And to have this property, it's linked to Fan-Shell conjugate. You must have divergence, which has some properties, and the properties are that you should go to infinite. The gradient of the function you're considering should go to infinite on the border of the simplex. And I don't know if something else than the entropy does the job regarding this. And I don't think that total work variation does it, at least.
All right, fantastic answer, Matthieu. Thank you very much. On this note, maybe we will move to Peter. Thank you again, Matthieu. If I can